Welcome to episode 23, BigQuery Fundamentals and Use Cases, where we explore how Google's serverless data warehouse enables analytics at scale. BigQuery was designed to handle massive datasets without the complexity of managing servers or storage infrastructure. It lets organizations focus on questions rather than configurations. By separating compute and storage, BigQuery delivers elasticity, so you can query petabytes of data quickly while paying only for what you use. This model suits everyone from small startups analyzing customer trends to global enterprises monitoring real-time transactions. In this episode, we'll examine how BigQuery stores, processes, and secures data, and how its flexible integrations and machine learning features make it a cornerstone for modern cloud analytics. One of BigQuery's defining characteristics is the separation of storage and compute. Traditionally, databases kept both tightly coupled. Data lived where queries were processed. BigQuery broke that pattern. Its storage layer is durable and independent, allowing data to persist even when no compute resources are running. The compute layer spins up dynamically to execute queries and scales to match workload demands. This design reduces idle costs and improves availability. For example, a business can store terabytes of sales records but pay for compute only when running reports. This separation also supports collaboration, as multiple teams can access the same data warehouse concurrently without interfering with one another's performance. Understanding tables, schemas, partitions, and clustering is essential to effective data organization in BigQuery. Tables are containers for rows of data structured by schemas, which define each column's type and name. Partitioning divides large tables into smaller segments based on time or integer ranges, making queries faster and cheaper by scanning only relevant data. Clustering further organizes data by selected columns, improving performance for common filters. Imagine a table storing years of event logs. Partitioning by date and clustering by user ID makes retrieval of recent user activity nearly instantaneous. These features transform raw storage into an intelligent layout optimized for both scale and speed. Columnar storage and distributed query execution make BigQuery exceptionally fast. Instead of storing entire rows together, BigQuery stores data by columns. This means queries that need only a few fields scan far less data. Under the hood, a distributed execution engine runs parts of a query in parallel across many nodes, merging results efficiently. The combination allows even complex analytics to finish in seconds. For example, summarizing millions of purchase records by region or category uses only the necessary columns, minimizing I/O and cost. Columnar architecture aligns naturally with analytical workloads, where reading many rows but few columns is the norm. BigQuery offers multiple methods to load data, including batch, streaming, and federated ingestion. Batch loading suits scheduled imports from files stored in cloud storage, ideal for nightly refreshes. Streaming inserts data continuously, supporting near real-time dashboards. Federated queries allow analysis of data stored outside BigQuery, such as in Google Sheets or cloud storage, without duplication. This flexibility means you can start small, then evolve into more automated pipelines as needs grow. For example, a retail company could stream live point-of-sale data while batching historical archives once per day. BigQuery's ingestion options adapt seamlessly to diverse operational realities. External tables and logical data lakes expand BigQuery's reach beyond its own storage. External tables reference data stored elsewhere, allowing analysis without physically importing it. This creates what's often called a logical data lake, a unified analytical layer across multiple storage systems. Teams can query structured and semi-structured data together, gaining insight without movement or transformation. For instance, analysts could join transactional data in BigQuery with clickstream logs stored in cloud storage. The result is flexibility without redundancy. This approach simplifies governance, since the source data stays where it belongs, while analytics happen in one consistent interface. At its core, BigQuery uses structured query language, or SQL, as its query foundation. Anyone familiar with relational databases will find the syntax familiar but extended for large-scale analytics. You can use standard statements like select, join, and group by, along with advanced functions for time, geography, and arrays. Because BigQuery adheres to standard SQL, existing tools and skills transfer easily. Analysts can write powerful queries to aggregate, filter, and visualize data without learning a proprietary language. SQL's readability also supports collaboration. Teams can review and refine queries together, ensuring shared understanding of how results are derived. Pricing in BigQuery follows a transparent, pay-for-use model. Storage costs are based on the volume of data stored, while query costs depend on the amount of data processed. For frequent workloads, reservations allow you to pre-purchase dedicated compute capacity, improving predictability. This flexibility encourages experimentation without fear of surprise bills. For example, a data scientist exploring a small dataset pays only for a few megabytes scanned, while enterprise teams with consistent demand may save by reserving capacity. Cost visibility in the console helps optimize queries and storage usage, making budgeting an active part of data governance rather than a mystery. Performance tuning in BigQuery revolves around efficient design rather than hardware adjustments. Pruning, clustering, and caching are key tools. Partition pruning skips unnecessary data, while clustering improves scan locality. Caching stores results from recent queries, returning them instantly when identical queries are rerun. Together, these techniques minimize compute consumption. For example, an analyst refreshing the same dashboard multiple times benefits from cached results at no extra cost. Query planners can also preview estimated data scanned before execution to adjust filters or projections. In BigQuery, performance tuning becomes a design conversation rather than a maintenance chore. Security in BigQuery relies on identity and access management, or IAM, along with advanced features like views and row-level access controls. IAM assigns permissions at the project, dataset, or table level, ensuring least privilege. Views let you share subsets of data without exposing full tables, and row-level policies restrict visibility within a dataset based on user identity or role. For instance, regional managers might see only data from their territory. These controls align security with business logic, balancing openness with compliance. Encryption at rest and in transit adds another layer of protection, reinforcing governance throughout the data lifecycle. Integration makes BigQuery a central hub for analytics. It connects easily with visualization tools like Looker, data notebooks for exploration, and connectors for business applications. This means insights can flow naturally into reports, dashboards, and predictive models. Analysts can use Looker for live dashboards, while data engineers automate data movement through connectors. These integrations eliminate silos and let organizations tell a single story across systems. When data flows freely between BigQuery and other tools, collaboration increases, and insights reach decision-makers faster. Integration turns data into action rather than isolated numbers. BigQuery ML, or machine learning, allows users to build and train models directly with SQL commands. Without leaving the familiar query environment, analysts can create models for prediction, classification, or forecasting. This lowers the barrier to entry for machine learning, making it accessible to anyone comfortable with SQL. For example, a marketing analyst can train a model to predict customer churn using historical data, then apply predictions in real time. By integrating ML within BigQuery, organizations bridge the gap between analytics and artificial intelligence without exporting data or managing separate environments. Common use cases highlight BigQuery's versatility. Businesses use it for financial reporting, real-time monitoring, and customer analytics. Healthcare organizations analyze medical records securely to improve patient outcomes. Retailers combine sales and inventory data for demand forecasting. Even public data sets, like weather or census data, can be joined with internal data for broader insights. BigQuery's scalability makes it suitable for both daily operations and deep research projects. The same engine that supports a single analyst can also power an enterprise-wide analytics platform. This flexibility turns BigQuery into an enabler of creativity as much as computation. BigQuery empowers organizations to extract insights with predictable performance and minimal overhead. Its serverless design, elastic compute, and intuitive query model transform how teams interact with data. Rather than worrying about servers or maintenance, users focus on discovery and improvement. Governance, performance, and cost control are built into its architecture, ensuring sustainable analytics growth. By understanding its fundamentals, storage separation, structured organization, security, and integration, you can design solutions that scale gracefully. BigQuery demonstrates how cloud analytics can be both powerful and approachable, enabling smarter decisions through simplicity and scale. Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.